Good morning, AOBI. This is Mr. Dunning. Stand by. I have news for you. And I have a math lesson. In today's lesson, we're going to look at 3 dimensions. And for many of you, this is a first in math. Although you live in 3 dimensions, you don't usually look at it in math. Today, it's going to be different. So, to get you started, if you look into the corner of a room, you'll see where wall sections meet the floor. Now, if we call that piece of floor an x-axis and that piece a y-axis, then the floor itself is the xy plane. This would be the z-axis. And bam, there you are in 3 dimensions in your own room, and you can see it. We're going to work with this idea, and we're going to see how it works out for circles, and tomorrow we're going to look at how it works for ellipses. Now, that's new too. So, stand by. Here comes 3D. Our first stop in 3 dimensions is going to be the equation of a cone. The equation of a cone is x squared plus y squared equals z squared. Now the x squared plus y squared should be a tip. Yeah, it's round. And we want that roundness to grow right up the z-axis here. So that's where the z squared term comes in. The equation of a cone going up the z-axis. X squared plus y squared equals z squared. If we cut through that cone with a plane, like that, the cross section that we get in that cutting plane is a circle. Let's take a look at that with a real simple manipulative piece of paper. My props here are going to be easy for you to understand. A piece of paper, which I'm going to roll like this, that's going to give us our cone shape. And yes, by the way, a cone results from wrapping a flat surface like that. And in some problems that you won't see this year, but you might see later on, you have to know that. Scotch tape. We need to glue our cone together with something. Otherwise, this little puppy is going to just fall apart. All right, here we go. We've got a cone. Now what we want to do with this cone is we want to cut through it with a plane. Now, that's going to be a little bit tricky, but I'm going to try with this pair of scissors to show you how this looks. And there we have it. We got through the cone. Now I think that you can see our cone is oriented like this. If we cut that cone with a plane, the cross section that we get is going to be a circle. And so the equation of that circle is related to the equation of the cone. And we're going to show you exactly how that works here. Stand by. Our next step is to choose a value for z. In other words, how high up do we want this cutting plane to be? In this example, I've chosen 3. So this cutting plane is 3 units above the xy plane. Going back to your room, okay, this cutting plane is 3 units above the floor and parallel to it. Here in the picture, it's 3 units above the xy plane and parallel to it. But what happens here in the circle? Well, now we have a circle in 2 dimensions, and we recognize it because if we put 3 in here for z, we get the equation of this circle x squared plus y squared is 9. And so using a cone and a cutting plane, we have the equation of the circle that is the cross section of the cone. What I'm trying to show here is that as we allow this cone that we had up there to move around the xy plane, the cutting plane, which is above the xy plane, has the image of a circle that appears to be moving around the cutting plane. But what's really moving? The cone. The cone is the thing that's moving. Let me see if I can convince you of that. In this example, we have moved the apex of the cone 2 units out the x-axis and 1 unit out the y-axis. That would be a point right about there in our picture. But we still have the cone. Same cone, the apex is moved. And when we do our cutting plane, the circle appears to have moved, and the circle itself now will have its center at x is 2, y is 1. Fascinating stuff. Now, if I asked you a question about all this, you should be able to answer it quickly and easily. I'm going to put the question up next. So here's your first question. A circle whose equation is x minus 1 quantity squared and y minus 3 quantity squared equals 25 is built from a cone whose equation is what? You should be able to answer that. But you're not done, because that cone is being cut by a plane at where? Now, if you've been paying attention, you know that that cone is being cut by a cutting plane. Got that? Cone is being cut by a cutting plane. So, this question wants the equation of the cone and where is the cutting plane. Let me give you a couple minutes to work on that. Straight line, piece of cake, right? Easy. I left up enough here to help you. You know the equation of the circle, okay? So what we need to do is plug those in here. That is the equation of the cone. And it's being cut by a cutting plane at z equals 5, because 25 is z squared. Making a transition from 2 dimensions to 3 dimensions is easy. You live in 3 dimensions. All that I'm doing is exposing you today to a little bit of the mathematical language. And it is just a tiny amount, because in a moment I will share with you a little bit about my background, and you can see why this is just a little bit. There are no real notes for this section, although I'd like for you to take notes, at least listen up. The first meaningful job I had was working for the United States Bureau of Astrogeology in Flagstaff. The Geological Survey, their job was taking the pictures that were taken of the moon and to map the surface of the moon based on those pictures. Well, there's a problem. You see, the problem is the moon is round like a ball, not round like a plate. You can't fall off the edge. It's round like a ball. And it has terrain relief, just like the Earth, mountains and valleys and craters. And we had to work off the shadows, the length of shadows. And in order to do that, we needed to use spherical trigonometry. Yeah, spherical trigonometry. That was my first real foray into 3 dimensions. But it got even more fascinating. The first meaningful job I had out of college, I went to work for Hughes Aerospace in Culver City, California. At that point, we were doing the Surveyor soft landing on the moon. And that had never been done before. Now, there's some fascinating projects, but one of the most fascinating was, how do you get from here to the moon? Because the Earth is moving in an orbit, the moon is moving in an orbit. You can't just draw a straight line. That doesn't work. So you've got 2 bodies moving through space. And you've got to get from one to the other, ideally in the shortest distance, because fuel is a concern, and you can't just gas up when you get to the moon. So, fascinating. And by the way, north, south, east, and west work pretty good when you're on this ball called Earth. But when you leave Earth, Dorothy, you're not Kansas anymore. North, south, east, and west don't mean diddly. So, how did we get that spacecraft from the Earth to the moon? How did we navigate? Well, I'll tell you right now, it was not using north, south, east, and west. We had to develop a whole new way of looking at how we're going to get from A to B. I'm going to let you think about that, and tomorrow I will share with you how we did that. Meanwhile, as always, you've been a great audience. I really hope that this opened your eyes and that you enjoyed learning about how circles come from cones and how when the circle appears to be moving around the XY plane, it's actually the cone underneath moving around. Tomorrow, we'll continue looking at 3 dimensions. Make it a great night. We'll see you all tomorrow.